Okay, welcome to everybody here in presence and also online. We are here for our ceremony of the Struttura della Materia Institute Prize, PRISM 2023, the third edition of this prize. So I invite here the director of the CNR-ISM, Dr. Antonio Crescenti.
Thank you, Aldo, and thank you for all your effort to have this third edition of our prize, this PRISM 2023. It's great that to see all of you here, and it's a pleasure to be in this very beautiful room, this Marconi's room, in this year that is the 100th year of CNR. So we will have a celebration in November. So everybody is welcome to join the celebration. This is the third edition. Let me say hello, first of all, to Federico, who is a very old friend, I must say. Unfortunately, time is passing fast, and Nicola, that is here. So welcome here in Rome, Nicola. Welcome, Federico, with the hope that this is the starting point for fruitful collaboration. Let me say just a few words about Federico and Nicola, for those that do not know them. Federico started in Rome in the 70s, getting his degree, and then he was traveling as everybody of us and going to US. And now he's professor, he has been professor and still is in the US. He did a lot of work on metasurfaces, and in our case, with quantum cascade laser that are used almost everywhere for infrared absorption spectroscopy. We tried to get one at ISM, but unfortunately it was not possible. But that's there is always some hope. And also Nicola is from chemistry and is at Imperial College in London, and is working mainly with organic photovoltaic and with application in very different fields. So I want to thank again all of you for being here, and in particular Aldo, that has done all the work to allow this meeting, and that everybody will be here to listen, and hope that it will be a very good future collaboration. So thank you.
Thanks, Antonio. This year, the celebration of the prize is within the anniversary of CNR. So we have a short video now of related to the first 100 years of CNR. Okay, thanks to the CNR for having these committed all this research for all these 100 years, and is also committed for making the research for the next 1,000 years probably. So I just spent 5 minutes to introduce the PRISM prize. And I would like now to go in presentation mode for the slides I have here on my laptop. And let's see if I can, okay, that's it. And we established as Institute of Structural Matter the Institute of Structural Matter of Istituto di Struttura della Materia prize in 2021. So the idea was to give a prize, an award, to those people, researchers, who were making outstanding breakthroughs in the past 5 years. So it's not a prize to the career. It's really a prize for those who are now, in the last 5 years is now, I want to say, are innovating, are promoting structural matter, are steering our future. So this is, and you see we have urgently need of people that can discover new science and define new sustainable, let's say, future. And so we, with PRISM, we would like to promote both fundamental and applied research in science, technology, or material and matters. It's a field where we are pushing ourselves very much, and we would like to, as institute, become a leader and an institute that could promote such kind of research. So we have two categories of PRISM prize. We have a senior PRISM intended for those who have aged more than 35 years. And you see, after 35, you become a senior in science, like in football, you know. And in PRISM, and also the PRISM Junior, intended for those less or equal 35 years old. And so how does it work? So we make a call. The call is among the scientists working in the field. This year, we actually extend even more. We invite entire departments of university to make nomination, and we had a lot of nomination this year. And there was an international jury made by the winner, the past winner of the PRISM Prize, as well the site responsible, which I'm very happy, almost all year. Some are very far in Trieste and were not able to attend, but all are present, and they all together, they were ranking, they were digging into the achievement this nominee got in the last 5 years, and then we got a final ranking and the final winner. So it's a long process. It takes almost 1 year, okay? But then at the end, we have winner, those who really improve the science of matter. So the prize is, you will see the prize, I will not anticipate, but beside the prize, we really like to offer the possibility to undertake a research together between the winner and the institute researcher, and also to offer our platform, our infrastructure to have collaborative research. So for the infrastructure, just I mentioned this, that's something that was developed in the last year, which is still in development. So we categorize all the tools, service, activity we have in the institute, and at the very end we see that, I mean, we have more than 134 tool service available, and this is the platform, a collaborative platform that we'd like to offer in the perspective that we really want to further develop science in the matter, in the science of matter, in the near future, also with the winner of the prize. So as you see, the infrastructure of model theory offers synthesis capability, analysis from the lab up to the synchrotron, and then also prototyping, more and more prototyping activities to use what we develop also in for applications. Let me summarize briefly the winner of the last prize. The first one was awarded by Valeria Nicolosi of Trinity College of Dublin and Matteo Mitrano from Harvard University. And then the second one was awarded by Riccardo Comin from Massachusetts Institute of Technology and Stefania Kakovic from CNR-ISM in Paris, France. So this year we are really happy and really honored to have Nicola Gasparini in the junior category and Federico Capasso in the senior category. So these two persons are, I want to really make this clear, not only have done, but are doing innovation and science and the structure of matter in matter. So are those people who really are pushing our knowledge beyond the state of art. So for us, it's really an honor to give the prize to this. Okay, perfect. So we to these people, and I'm really happy that also the president of CNR is coming also to us to introduce the president of CNR, professoressa Maria Chiara Carrozza. So, President, as every year we are giving this award to two persons, two scientists, which are now developing science in the field of structure of matter, and they are promoting science, and they are developing beyond the state of art. So is the PRISM prize, as I was briefly mentioned, is a prize for those who are now doing science, and they are pushing the science and our knowledge beyond the state of art. So this is also the commitment of CNR, and for this reason we have this year this celebration and this award ceremony within the 100th celebration anniversary of CNR, the 100-year anniversary. So I give you just a word.
So good afternoon. We are online also, I guess. Okay. So good afternoon, everybody, and thank you very much, Aldo, for inviting me here. It's simple because I am few meters from this room, so I didn't make any long travel for coming here. So it's a pleasure to know, to understand that this year we have two Nicola Gasparini and Federico Capasso. You are here, I think. No. Federico. Yeah, and Federico Capasso, and it's a pleasure to be here and welcome you here in this building. We are at the end of a long roadmap for celebrating the 100 years anniversary since our foundation. Yesterday afternoon, we celebrated in Berlin with Max Planck. Max Planck was celebrating 75 years old since foundation, and we were celebrating 100 years since foundation. So we were together in order to discuss about how science today is developing the future of the human species and its relationship with the planet, and how science is fundamental to understand many answers to scientific questions like climate change, the origin of life, astrobiology. We have a lot of things, dark matter, and a lot of scientific questions attracting the interest of young scientists. And so it's a pleasure to be here and also to celebrate this prize. You call it prize, PRISM. PRISM. And on the Institute of Structure of Matter, you say like that. Okay, I am a physicist by chance, and my background is in high energy physics, so I love physics very much. And also I love this idea of giving some prize and award to scientists, because this is based on peer review, because this is a way how the community select and emphasize the results and achievements in science. So I think it's important, and also to encourage people spending the entire life in trying to develop projects. And so when there are achievements, and these achievements are recognized by peers, and the community gives an award, I think it's an important moment for celebrating everybody's working in science. So it's a way of saying science is important. We recognize the achievements. Achievements are fundamental for the progress of science. So congratulations to Federico and Nicola from my side, and ad maiora, I can say in Latin. And thank you for being here, for celebrating this time, and also for celebrating 100 years since foundation of CNR. Thank you very much.
Thanks, President. We took your invitation last year to come in presence, because last year was online, and then you say, Aldo, you need to do in presence, and then we move on, and so we did it.
I also promise I will come to Tor Vergata.
Thanks.
We will define the date.
Thanks a lot.
Because I know that I have to come. So thank you very much for being here.
Thanks a lot. So it was really a pleasure. I mean, the President is supporting all this activity, and then also the future of CNR. So we have an incredible plan for the future of CNR. Then stay tuned. You will see very interesting development. And so this is the prize for these people, but these two research. But before, so we asked them to do a little job for us. I mean, to present their innovation. So to present the science and how they are pushing the science before what we actually know. And for this reason, both Nicola Gasparini and Federico Capasso will present two seminars. The seminar will stay for 25-30 minutes, and then we have 5 minutes for questions. And then we move on to the award ceremony. So I invite the first speaker, which is Nicola Gasparini, and who will speak about from UV to near-infrared light detection, next generation photodetector for imaging and biometric application.
Thank you very much. All right, so before I start, you prefer to go without? Or without? Without? Okay, it's fine. So before I start, just want to, to thank you, Aldo, and to be here. I was very, very humble to receive this prize, and can't wait to, to show you what I've been doing and I've done in the last 5 years. But before I start, I just want to, a little joke from my side, because I just spoiled this information yesterday and today. But I don't know if you guys know, I started at CNR. So I was born at CNR in 2013 at ISOF CNR in Bologna. And that's where my journey started. So before I start today, if it's possible to put my presentation on, that's the one. So I think it's important that, let me just put this one on. Just before starting, I think any prize that you get is not an individual prize. It's always coming from a very huge team effort. And here we have a lot of people that have been working with me at Imperial. That's my group with the people there, my collaborator, but also around the world. So I started my journey away from Italy in FAU in Germany with Professor Christoph Brabeck. I'm going to show you a few slides of what I've been doing during my PhD, and then my journey in continue as a postdoctoral fellow at KAUST with Professor Ian McCulloch and Dari Baran. And then I moved to Imperial College, where I started my independent career. So that's that one is the framework that I want to start with. And then without any further ado, I just want to deep dive into science. So if I look to that one, what I'm going to talk about to you today is this beautiful technology called thin-film processable electronics. And what I have here shown here is I'm going to start with organics. So I don't know how, I think the audience here know very well what organic material are. They can be printed from solution the same way you print newspaper. Aldo is one of the best one in doing that for dye sensitize the beginning and then perovskite. And what I really like very much is also it's lightweight. So for example, if you wear something like a smartwatch, you know, you're full of these electronics at your wrist. And if I start with organics, I want to introduce that. Just that one is important that we keep it for being at the same pace. So when I talk about organic photovoltaics or organic photodetector, I'm calling about an electron donor and electron acceptor material put together in solution to form the so-called bulk heterojunction that you see here. And basically with this technology, what you do, you are able theoretically to convert every single exciton that has been formed in your photoactive layer into charges. And a lot of this technology has been done by looking to donor material. You see here the workhorse for electronics, P3HT, but of course, and PCBM as N-type material. However, luckily, the field is not anymore driven by the materials. We have the so-called non-fullerene acceptor here at DTBR that I'm very proud to always to show that, since I was like at the beginning of that field with Professor Ian McCulloch. And I don't know if you know, but everything started by a mistake. I always say that one in the laboratory of Kodak, where they thought, all right, we're doing organic light emitting diodes. They emit light, but what about if now I shine light on it and I extract the charges? And that one is the first tank cell that was working about 1% efficiency back in 1985, which I was not even born. And then people already were start publishing these papers. As I said before, the field moved very, very quickly from 1985 to 1995 in about the course of 10 years, where there the efficiency was skyrocketed already because they thought about putting these two materials together. And in that way, the interfacial between the donor and the acceptor material was not anymore like on top of each other, but actually throughout the entire bulk. And that's what I've been doing in the last, let's say, 7-8 years. So that's going to go very quickly because I know the price about my last 5 years. So that one is going to be just an overview to show you and also to foster collaboration, because if you want to work in organic photovoltaics on solar, I'm there. So I'm still working in this field. In particular, during my PhD, I started to look into charge recombination processes. So I really wanted to know what's going on in the charges before they recombine, because in that way, I think you can discover a lot. In particular, in these papers there, we look into the fullerene versus the non-fullerene acceptor materials and figured out that non-fullerene acceptor-based OPV, so organic photovoltaics, were showing very interesting in terms of charge recombination, way more similar to perovskite and silicon. And for example, one of the proudest papers that I've ever done, it is that one. So we know from thermodynamics that a good solar cell should be a good LED. And for many, many, many years, that was not possible. However, that one is a real 10% efficient devices, which is emitting light. So we show that that one is possible. And for example, and Aldo know that very, very well, that if you want to do upscale devices, you want to have it thick. Because if you want to put in a roll-to-roll coater, forget to use 100 nanometer. You want to use like half a micron. And that was an example where we were able to show that it's possible to maintain the high photovoltaic performances in the course of the thickness. So that was like a good achievement. As I said before, I really like about recombination. And for example, one another question mark that they always had is about why organics cannot attain the same fill factor as silicon or perovskite. And then I thought, okay, as a chemist or material scientist or physicist, I don't know what I am, but basically I thought about putting together 3 materials and in that way try to really suppress charge recombination. And that was one of the first examples with organic photovoltaics achieving over 77% fill factor, which is one of the highest reported back in the day. And the same concept I've been using for improving photostability. So that one, again, important because if we want this technology to be commercially available, we need to make it stable. So I think that is where the field should go further. And especially in degradation, that one is like a homemade setup that I had it in the Christoph group, where we were probing the combination of these charges. However, as I said, we're talking today only about my last 5 years. So I joined Imperial College 4 years ago. So kind of, I'm going to show you what I've been doing since I went to the island. And basically, I decided to change a little bit the gears. So moving from photovoltaics to photodetector. Why that? Because I think a lot of people know that how expensive is inorganic technologies, right? If you look to the visible, there is no game. Silicon is the best, right? So that only works very well. You can get it cheaper. However, as soon as you move away from visible, you go to UV, you go to near infrared. It's very, very complicated, right? Because it's also very expensive, especially the UV is all by cesium iodide and cesium telluride. Wherever in the infrared, we all know how expensive is InGaAs detector. And then I thought, okay, but I've been using a lot of this material. And actually, by chemistry, we can easily modulate the absorption all the way from the UV to visible to infrared. And this example here that I've shown here is actually just by changing the molecular structure, not really getting to novel completing materials, but more looking to slight modification that chemists can do, not myself. I normally do devices, never done synthesis in my life. However, as I put it here, this can be potentially low cost. I know it's a little bit complicated to say low cost at the moment when we pay about 1 grand per gram, but we're getting there, we can get it. And in particular, I'm very interested in the infrared part of this, of the light spectrum, not solar spectrum, but light spectrum, in particular because infrared photodetector open up the biological window, in particular near 2 and near 3. And you know, there is offer a very high, deeper tissue penetration. That's important, right? Because again, if you want to get more information about our body, we need to go in depth. Otherwise, it's going to be complicated. And in particular, near-infrared photodetector, they're conformable, they can be biocompatible. There is no really need for cooling. That's another big advantage compared to InGaAs. In InGaAs, we know that we need to cool down to 77 Kelvin to make it working. For organics, you don't really need that. And they can be also used for health monitoring. I'm going to show a couple examples later, so bear with me. And in particular, there are different ways. So I'm not the first one, of course, showing that it's possible to do near-infrared photodetector. Other people have been using that in the past or currently by playing with internal filtering or external, playing with the so-called charge transfer states, which is something that I find it very cool because the charge transfer state for the spectroscopy is here, is something that you don't want in organic photovoltaics, but actually for photodetector, you can use it. Or by charge collection narrowing, which is basically making the device very, very thick, and then harvesting the charges at the back of your electrode. What I'm doing, I'm going to do with chemistry. So you're going to see in a bit with material science. What is a photodetector? It is basically a solar cell. However, instead of extracting the charges, the 4th quadrant of the JV characteristics, we do in the 3rd quadrant. So we want to maximize the light to current conversion, similar to a transistor, getting basically all the charges out in reverse bias, which again is very important because in that way, the electric field is our friend. So we can easily extract what otherwise would recombine. I just bear with me 2 minutes on that because I'm going to introduce a couple of figure of merits because in photovoltaics, we only speak about power conversion efficiency. However, in the photodetector, we have 7 figure of merit. So I'm going to discuss a little bit about that one. So responsivity is basically EQE, so the external quantum efficiency per wavelength. We want to know where and how we harvest the charges. The dark current, very, very important. So basically is the current in the darkness. And that one is the one that defines our lowest, basically, rate in order to convert light into current. Rise and fall times, we care about that one because, for example, if you want to go for video application, you want to have a camera which is fast. Similarly, you want to also have a camera which is very able to differentiate between light and dark. And that one is the so-called noise equivalent power, which is basically the minimum amount of light that you need in order to see a signal. The cutoff frequency is sort of rise and fall time in a way. It's basically what you look into, for example, in the specs of most electronics that you have, is normally the value where your signal drops by 3 decibel. Again, just to give you a number, for slow video application, 10 kilohertz is enough to have a video application. And the last one is the linear dynamic range, because, for example, if you want to look into this amount of light, which I guess that when we're talking about 1,000 lux, something like that, maybe a little bit more, basically you want to have the response of the light that is going to be linear by decreasing this light, for example, to 200 lux. Again, important for different applications, which Aldo knows very well on indoor. And the best figure of merit is that one. So if you want to compare all your photodetector, the specific detectivity is the one that defines each electronics. And again, that one is defined as basically your noise equivalent power with some sort of factor. I'm not going to bother you with the nomenclature here, but just keep in mind, the higher the better, similar to the power conversion efficiency. As I was saying before, there are different approaches to suppress that current. And people are playing with materials energetics, and I'm with them. You can also play with active layer thicknesses. Again, you can imagine that you make a very thick device, you're going to maximize your shunt resistance and minimize your pinholes or defects that you might have in your active layer. Or also play with hole and electron blocking layer. That is important because of the same way, if you avoid the opposite charge to go inside your bulk, that will be a good way for your dark current. Where I started, again, I think in science, most of the time you start from something that you were not thinking. So I started this field, entering this field by playing with this non-Fourier acceptor from Ian McCulloch. In particular, we have there like the variation of this FBR, the FBR, the TBR that we published now back, wow, 2016, already 7 years ago. And basically what is important here is showing the absorption profile. You see, again, by playing with chemistry, we are able to move the absorption where we wanted. And in particular, I was in Erlangen, and I think most of you might know that in Erlangen, where I had the Siemens headquarters over there, so it was very easy to knock on the door of the people at Siemens and say, guys, I have this material, it's working very well for indoor photovoltaics. It had a very low dark current. Do you want to try out a photodetector? It exactly went like that. And so I went there, I think with my 2 ml of solution, and spray coated there on top of ITO zinc oxide. I'm going to show the structure later, and get very low dark current on a spray coated device on a 5 by 5 centimeter substrate. So again, very important for upscale production. And if you are at Siemens and you have a photodetector that is working, we tried immediately to do an imager. And that one is not a photodiode, it's actually an imager. So it's a photodetector constructed, fabricated on top of a morphosilicon TFT back panel. So what you see there is an image between the photodetector and the light by a 256 pixels. So now we are able not only to get a photodetector performances, but actually to get also an image out of it. So that was kind of the beginning. And again, I always have to show that one. That's what they told me to do. Basically, that one is the so-called MTF. So it's where you put a sharp edge between light and the detector, and you want to see light and dark in the course of 2 pixels. So pixel 1 will be light, pixel 2 will be dark. And actually, by doing the Fourier transform of that one, the resolution was exactly 2 pixels. So we're able to really make a very good imager. And then I started my journey. So basically, we thought about, okay, can we improve even further the P3HT and the TBR photodetector by playing with novel material, PTQ10, the polymer that is there. No, that one is not working anymore. Anyways, the polymer on the top left corner for you guys, there is a material that has been also known in the photovoltaics field to be working well with thick devices. So it was also very easy to make a detector out of that with the condition I told you before. And what is interesting to see here, you see basically in the responsivity graph in the middle, the red curve, you see is not anymore the very infrared material. It's more like is more like absorbing all the way from 350 to 700 nanometer. And for somebody that has a good eye and knows the silicon detection, actually this is even better than the SV100 diode that we are using for the calibration of the NICV, for example. However, it was not working very well in the infrared with the TBR. And I'm going to show you in a second the reason for that one is because we didn't have a good offset for all extraction. However, this is a slide that I really like. If you look again in the power that we use for these devices, so 0.57 microwatt per centimeter square is basically maybe 1,000 times lower light intensity of what we have now in this room. But despite that, I was able to detect signal. So again, that's what thanks to the low dark current. I like to do upscaling, and likely I have a Blake coater there and large area devices. So now it's on a 5 by 5 centimeter substrate, and we were able to get similar performances on a 1 square centimeter pixel. Again, important if you want to upscale also this technology. During my PhD, I work a lot with ternary. And when I speak about ternary, is making, again, either 2 donor and a scepter, to a scepter and 1 donor together. And I thought about, okay, if in the case you see here in the blue that IDTBR is not able to extract the holes through via HOMO of PTQ10, but FBR can, what about I put together these 2 material? And that one is the concept of ternary that likely was basically my PhD thesis, working on ternary OPV. And in ternary, it's quite interesting because, again, the position of the third component is super important to change the recombination processes. And in particular, if it's embedded in the donor, in the scepter at the interface, you can modulate whatever the physics that you want. And then basically, okay, if I put together in a ternary OPD, can I actually get out these charges that are otherwise trapped in a DTBR? And actually it worked. So that one is just pay attention on the responsivity curve there, because the green plot over there is showing improved photoresponsivity at 700 nanometer by using 50% of the initial material. So again, it worked, and that was a nice study. We understood like basically why that one was happening. And this one to look into the detectivity. So before we're having, okay, very high detectivity, but limited by visible. And now with this ternary blend, we were able to move it all the way from 350 nanometer to 750 nanometer with a detectivity of 10 to the 12 joules. So that was kind of where we started. The title was Near Infrared Photodetector, isn't it? And so far, it didn't show you a lot of infrared. And that's where Paulina and Christos on the top came into play. So we start looking into these push-pull polymers, TQT. Again, due to this push-pull hybridization, this polymer allows very infrared absorption. You see here, absorption maximum at about 1300 nanometer. Again, if that would work as a photodetector, would be happy days. So luckily, we have the possibility to combine with different non-Fourier acceptor, in particular here Y6, well known in the field, and the IACO4F. Funny bit, if you are in this field, for the first time in my life, the infrared material is not the acceptor, it's actually the donor. So that was like very interesting to start with. We made an inverted structure device, nothing crazy, like just to be a sort of proof of concept. And what we observe is like very high dark current, expectable, because if you work in this infrared absorption, you would expect thermalization to play a big role. Charges are hot over there. However, if you check there the responsivity, you see there is a nice pump at around, starting from 1000 to 1600 nanometer. So the photodetector is working in this infrared region. And if you look into the detectivity, not anymore 10 to the 12. We need the next 5 years when I'm going to become senior there to try to get higher this detectivity there. However, again, it was kind of the first example to show that now the absorption or the detection is possible from 400 nanometer to 1800 nanometer with one device, not anymore combining different technologies. Interesting linear dynamic range, again, are of about 46 decibel, but and very good actually cutoff frequency. So again, this number I'm going to jump quickly because are okay, are about 100 kilohertz. Again, as I said before, video application 10 kilohertz are enough. So now we are more looking to the 100 kilohertz. What I want to show you is here. So I put back this slide yesterday after our dinner. So that one we've done transit absorption spectroscopy on the 2 blends to understand why the IACO4F blend was working better than the Y6 blend. And what we've done here is probing the visible in this particular case and looking to the bleach. So looking to the photo bleach of the donor material absorbing there. And in particular, we'll try to understand if the charge transfer going from the donor to the acceptor is improved. And when we look there, the TQT ISC4F on the top corner, you see that the charge transfer is about twice as fast as in the case of the whole transfer compared to the Y6 case. And that we believe is the reason why the detector is working better in that blend. And of course, that one is due to morphology. If you look to the morphology, I hope you can see that in the case of the TQT ISC4F, everything is more intermixed. You see these white balls and black, a little bit more intermixed compared to here, where you see very big islands of white. We don't know if it's the donor or the acceptor, but basically you can imagine that if you have a charge sitting in those islands, they will recombine because they cannot find the percolation pathway to be extracted. And I'm going to show you just an example of that, because if you have a detector that is working well in the infrared, you want to have an application. And what we thought is about, okay, what about now I put my finger between an infrared laser, infrared diode, not a laser, like the classical 3 milliwatt diode, and the photodetector, without having any oscilloscopes, nor any lock-in, nothing there, just by looking in the current as a function of time. Because as you might know, the level of hemoglobin will absorb differently if it's oxygenated or not oxygenated. And that one is the multi-million pound instrument that we built it up in the lab. I think that one is like maybe less than 1,000 pounds. Maybe the oscilloscope, it's the most expensive bit in this, where literally I was placing my finger between the detector and the light source. And that one is my heartbeat. So that one is my heartbeat in real time, where it's clearly we can differentiate between the two parts of hemoglobin directly there. And that's also at 880 nanometer, at the 1050 nanometer to probe the two different materials. So that was kind of very cool, to be honest, to be in the lab and doing this experiment. We tried a lot, like, for example, doing push-ups and see if my heartbeat was going up, just to see if the detector could respond faster. And he actually was doing the support information. There are a couple of these information. Can we make it better? Yes. So I went back to my chemist and say, okay, now can you modify the material and making more rigid? Because we believe that being too amorphous for the previous material was the reason of recombination. And then we went to TQT to TQ3T. So we just added two thiophene, nothing crazy. You see there, but we were able to modulate quite well the energetics, make a little bit wider gap. And you see the curve in the blue in the middle. And that one, basically, we clearly see that the method was improving, because by looking at the 2D GWAX plot and the 1D GWAX plot, basically what I want to show, you see already from the color, you have more scattering. In the case of TQ3T, the material is more crystalline, likely the transport will be better. And exactly what happened. Now the dark current reduced by 1 order of magnitude. Great. The detectivity went up. So, okay, we're not going anymore to 1800. We were stopping at 1400, but 10 to the 10 again achieved. Very high cutoff frequency. So now we improved by a factor of 3, basically the cutoff frequency due to improved mobility, and the noise equivalent power by a factor of 2. So everything was like a very good stepping stone. And what it was very cool is now that, so not only were able to detect my heart beat, but also by playing with the first and second derivative, we were able to get that not exactly the sugar level in my blood, but we were able to get like sort of threshold to say if you're a diabetic or not. Again, from a device that you can prepare in your lab with an area that is not so big without any difficulty in readout. It's just current connected to a Keithley. And that, again, we went even further on spectroscopy. There, poly was getting a little bit better. You see here now the spectrum is all the way to 1600 nanometer. And again, this 3 picoamp that we were seeing before, picosecond we were seeing before, now is about 1.3 picoseconds. So again, the charge extraction was even faster for this material. Again, all goes together with the previous one. I'm going to stop with the organic just by showing that one. That one is a work that I started during my postdoc at KAUST, together with Achilleas and Shaika, when I was doing the postdoc there. And then they asked me, can we actually coat neurons on top of organic semiconductors? And I said, I have no idea, but I can tell you that if we work in open circuit voltage, this material, they do have a voltage. even at VOC, right? And in particular, some of these material, TSC on the top and PDCBT on the bottom, they're very robust to working together. And what we've done it there, and the paper was just, I think it was accepted a few weeks ago. So very, it took 4 years, but 5 years actually. But we made it. And from going from the top to the bottom, basically we have done a live dead assay, and to show that basically the neurons were happy on top of organic semiconductor. Great. Number 2, patch clamp measurement to see if you have depolarization of the neurons upon light illumination. Again, that was clearly from the bottom graph, where you have membrane potential recording and action potential generation in these devices, again, at open circuit voltage. So that was like a good, showing that it's possible even to go further into bioelectronics with this concept. So that is kind of the first summary of OPV. If I still have 10 minutes, I'm gonna carry on the last bit that we are doing also in the group, which is basically perovskite. So I think I don't have to introduce this material. It's great, changed the field of photovoltaics dramatically. We're talking about 2,000-3,000 papers a year, maybe even more, to be honest. I was Googling perovskite photodetector, was about 1,300 papers a year. And in solar, most likely there are even more. So we're talking about an ABX3 structure, similar to calcium titanate, where, again, that one we call it a chemistry or material science playground. You play with the halogens, you play with the cation, you play wherever you are, and you move you can modulate the absorption and the properties as you want. And we thought, okay, this concept is really working for photovoltaics. Why not using for photodetector? And these 3 guys there in the bottom thought like, okay, now let's try to play with the iodine to bromide ratio to move the absorption and the open circuit voltage. So we made a PIN structure, very easy, with the self-assembly monolayer as a P-type material. Classical mapping with, as I said, like by playing with the iodine to the bromide contribution. And what we observe is exactly what the literature was observing. You add bromide, or you replace iodine with bromide, you enlarge the band gap, the absorption is more towards the visible. However, the dark current went down very much, by almost an order of magnitude. And that one is a nice correlation, because the open circuit voltage increase, you see there from the top part, and there is a correlation with organic photodetectors, where the higher the open circuit voltage, the lower the dark current. And I think this one is a bit, you cannot really say that one in general terms, but that's an observation. Of course, if you enlarge the band gap, if you have, let's say, a hole sitting somewhere around 5 electron volt, it's going to be very difficult to go in the opposite side of the electrode. So, but it's not only that. Otherwise, you will have like a massive cesium iodide, maybe perovskite, but it's going to be very at 3 electron voltage. You're not going to harvest a lot of light there. We got noise spectral densities that were almost as low as the oscilloscope. So again, almost no noise in these devices, not anymore at -2 volt, more at -0.5. We're going to get to this point because I think in the future, we don't really know why perovskite cannot stand at 2 large reverse biases. We're working on it. But what is important is here, you see that basically now we were able to improve the detectivity, again, just by playing with bromide. I found it very fascinating. As I was telling you before, I don't think it's only energetics, but there is also a lot going on charge recombination. And in particular, what we've done here is transient photoluminescence, where upon addition of 15% of bromide, we're able to almost improve by a factor of 4 the charge current lifetime. Again, we think about that one because you are turning down trap-assisted recombination. And of course, by playing also with the morphology. So what we're seeing here with the 15% bromide, we're able to get like larger crystals on the top use SEM images, which with very nice grains. And that one, again, we know that if you're able to enlarge the grains and get into interfaces that are more prone for charge destruction, you will have better photodiode performances. Exactly what we observe. And the last bit, because I'm not running late, this is one of the last 2 slides, where if you, again, working on the field of photovoltaics with cesium, with formidinium lead iodide, you know that it's not stable because the alpha structure, the alpha phase will turn into delta. And that one is very problematic because not only the color changes, but it's not stable. And then we thought, okay, cesium addition is something that people are doing to stabilize that. Is it also possible to look into the cesium addition and stabilize dark current? And that's what Eun-Young and David have been doing. The paper is just submitted. And basically what they've done there, they look first of all to the Williamson Hall plot, especially looking to every single diffraction or scattering you see from X-ray. And basically the strain is clearly reduced upon addition of 5% of cesium. And that resembles on lower dark current for these devices. So again, what I want to, or hope you, I'm convinced you today that I'm not inventing anything new, basically, but I'm getting a lot from what we're doing from photovoltaics and applying in a new field of photodetector. By getting this information, I think we can get there. In particular, and this one is the last slide, we're also making stable in over 30 days. So that one is an XRD measurement done after 30 days in air, showing that it's possible to have maintaining the alpha phase in cesium FAPE photodetector, whereas the cesium 0, so without, so basically on the pristine FAPE, showing the delta phase there you see on the bottom plot, and also the dark current was maintained in these devices. So with that, I'm gonna stop my presentation, and I'm gonna say a big thank you to the people that made this work happening, especially at Imperial. That's my group in one of the group meeting we had last year, and of course you for your kind attention. Thank you very much.
Thanks a lot, Nicola. You were touching many of the activity we are doing also in the institutes, from spectroscopy, ultrafast spectroscopy to chemists, and then also to device. So now, is there any question? There is a question over there. I'm just jumping here.
Thank you. I've seen a lot of interesting things, as Aldo said. We do more or less similar things, but I want to ask you if you use as a routinary tool for the screening, especially for the synthesis of small molecules for all these applications, atomistic simulations. You didn't speak of this, and I'm interested because I'm a theoretical chemist.
That's why I still getting ab initio materials there is a bit tough. And what is very, very difficult is especially on the side chain of these new small molecules, especially because you can make like a beautiful push-pull linear NFA. However, it's going to be tough to really make it solid. So that's what we, what we do normally is like a lot of DFT calculation to see like how the bandwidth changes, but that's very preliminary, and I don't think that is the right approach. So absolutely very happy to get anything you might propose.
Okay, thank you. But we perform very nice semi-empirical simulations to tackle such problems.
Very impressive presentation. I was wondering, our institute is very much involved in diagnostics. So we have many tools that can be used in this case. So I was wondering if we have thought about some kind of application in our using our tools.
Anything that is very light, yes. What I really would like to enter is the X-ray detection. So that I really would like to enter into that, because especially crosscut can be very good into X-ray detection. So yes, would be very nice to look into that together.
Okay, let's thank Nicola again, and thanks Nicola, thanks a lot. Don't move. So Nicola, don't leave the room. So now we go to the next winner. In the senior category is Professor Federico Capasso, And Federico, it's really a pleasure to have you here. And the title of your talk is Designer Materials from Quantum Cascade Laser to Flat Optics. Thanks a lot.
Thank you very much, Aldo, for the introduction. I'm really honored to receive this prize, you know, particularly because I was educated in Roma, and that's my alma mater, the University of Rome. So again, thank you very much also to the CNR for this award. And I'm going to start from work that we actually is well beyond the 5 years, but the reason I've combined the quantum cascade work with actually the more recent flat optics work is because the beginning of flat optics actually was totally from a serendipitous thing that happened, which was in the context of quantum cascade laser. So one of my distinguished colleagues asked me a key question, and that got me started in a completely different direction. And I will explain how that happened. So the quantum cascade laser was actually born out of the work that I've been doing at Bell Labs we collaborated with 25 years with the inventor of MBE, which is Alfred Cho. So I arrived at Bell Labs in '76, and within a year or two, I got fascinated by the possibility that MBE had, which at that time, really, there were two laboratories doing it at really high level. One is Bell Labs, and the other was IBM at Yorktown Heights, the group of Leo A. Saki. So the idea here is that you can view this as spray painting atoms in a high vacuum chamber. So you can literally grow an atomic layer on top of each other. The way you do this is not only in high vacuum, you have cells which contain the elements of the, say, semiconductors you want to grow, like gallium arsenide. You can shutter these cells you can turn them on and off so that controls the layer thickness, and the substrate is kept at high temperature so the atoms can run around essentially and reproduce the underlying crystalline substrate. And I think it's fair to say that MB opened the possibility of creating artificial material with man-made properties, both for electronic application and optical one. So, I mean, this was one of the early TM pictures. In fact, it's a TM of a quantum cascade. This on the left. I'm talking about now of a quantum cascade laser where the thinnest layer was basically around 7 angstroms. And the key point was, even from the initial TM picture, the extreme abruptness of the interface and also the actual smoothness. So the quantum cascade laser is a device, a laser that now can cover the entire spectral region from the mid-IR up to basically terahertz, which actually a better name for it would be far infrared. And until then, there was only really one laser that could capture just a few selected wavelengths, and that's the CO2 laser. Plus, of course, there were these molecular lasers, which, however, had problems of bulkiness and so forth. So this was our first paper in 1994. Again, it's at the end, people are the most important resource, and here I want to acknowledge my collaborator, Al Cho. Here on the right, getting the Medal of Science from MBE, from President Clinton. You can see that Clinton is a real giant, okay? And to the left here, I have two now distinguished colleagues that were postdocs at the time. Jérôme Feist, a professor at the ETH, Carlos Sirtori, who is a professor at the École Normale Supérieure in France. Claire Machel is very distinguished professor at the University of Princeton. She was also a postdoc then, and Debbie Sivko was the assistant of Al Cho for basically over 20 years. So the quantum cascade laser essentially creates a cascade of electrons that at each stage can emit an actual photon. And you can see this in this movie here. Now, this on the right-hand side shows a more realistic type of band structure. So the key point, you have a repetitions of injector regions and active regions. So you can inject your electron from a dope injector here into an undope active region, where you artificially create a population in inversion between these two red states here. Essentially, you design the population in version. You have to quench tunneling out here, and you have to empty this state so very fast. So to do that, this doublet here is spaced by precisely an optical phonon energy around 30 millielectron volts. So the electron in the lower excited state can relax extremely fast in a sub-picosecond time to the ground state, and then can tunnel out. And this, in fact, is a waveguide structure. Light comes out from the facet here. Again, the key point here is the following, and this is really different from all other lasers. If you want to change significantly the laser wavelengths from all existing laser, you basically have only one choice. You have to change the material, basically. There's no other way. Here, with the same combination of materials, let's say aluminum indium arsenide, which is a ternary alloy, and gallium indium arsenide, a precise composition at which their lattice match to indium phosphide. By just changing the thicknesses of these layers, you can tailor the wavelengths from, let's say, 3.5 micron up to basically well into, let's say, 15, 16 micron wavelengths. So this tailorability of the wavelengths is very significant. There are also methods to actually tune the wavelengths given an existing structure. If you can design a broad gain spectrum, then there are techniques like using an external grating, and you can rotate the grating. You can get significant tuning of the wavelength. In fact, there are commercial products out there in a box, basically, that contains an external cavity quantum cascade laser. What you can also do, and this is shown here, if you are interested in just the very precise wavelengths, you can put a grating on. This is called distributed feedback laser. It's a well-established technique to get single mode in telecommunication laser. We and others have used it also for the mid-infrared. So, and the key point, you know, this is fabricated with standard semiconductor processing technology. In fact, if you look at laser like this just from the outside, without looking at the cross section, you basically make a good guess if you said this is a conventional semiconductor laser, with an exception that these tend to be longer than the telecom laser. So the key point is that the reason of the success of the quantum cascade laser is because it covers the so-called molecular fingerprint region where most molecules absorb light. So this has application, wide application in sensor and in spectroscopy, and here I've listed some of the things. And in particular, I will show you, because this work is carrying out to the present day as we speak now, application for this in the environment, atmospheric chemistry in particular, and understanding the chemistry of the atmosphere is important for models of climate change. And I've been fortunate because here at Harvard, we have world-leading groups in these areas that in fact are using quantum cascade laser. Here is just a bird's eye view of the application of mid-infrared technology. Beyond also what I just said, of course, for security type of application, thermal imaging, standoff detection. Standoff means if you want, for example, to examine the spectrum of a contaminated surface and you don't want to get too close because there might be some hazardous materials, you basically project a laser and you look at the reflection, you look at the reflection spectrum, basically. Also, they are starting to be used for industrial monitoring and so forth, biomedical sensing, and so forth. So the spectroscopy is very simple. Typically, you want to use a cavity with a long length, which means really a multi-pass cavity, because you might want to detect down to levels of part per billion in volume. So you need to make up for the low concentration by achieving multiple passes. Okay, and we have collaborated over the years, my group, both when I was at Bell Labs and when I moved to Harvard, with many groups in spectroscopy and chemical sensing. Now I want to start to give you a bit of what QCLs can do for atmospheric scientists. And so this happened, in fact, quite recently here. But if you look, we know that in around September, the Arctic sea ice volume reaches an actual minimum, okay? And basically in around this time here and beyond, now there is a time, it doesn't last long, where essentially you have the majority of the ice melted. Now this is a very serious problem, and this is basically due to feedbacks. You see, as my distinguished colleague Jim Anderson always say, we often emphasize too much our attention on just the increase in temperature. I mean, the underlying cause that eventually could give rise to some major disaster are the feedbacks. What are the feedbacks? This is a typical feedback. We know that the Arctic ice reflects light. As however, due to the greenhouse gases, okay, there is more ice melts, that increases the reflectivity, decreases the reflectivity, therefore there is more heating. So you get into a positive loop, and there is really not an easy way out of it, okay? And so it's really something to be concerned about. And so I want to start to discuss, and this is basically has been ongoing work by two colleagues. One colleague is Stephen Wofsit from Harvard, who has flown in a Gulfstream aircraft, okay, planes basically from the low latitude to high altitude, and also in the longitude. And what this does, this plane goes up, as it goes up, also changes the altitude, so can get the latitude and altitude profile for significant gases. These are not only the greenhouse gases, but gases like CO, carbon monoxide, and so forth. Of course, methane, N2O. So I was able to detect these are the typical concentration. And the important thing is the precision of the measurement. You see, it's really an outstanding precision down to a fraction of a part per billion. So they get these altitude profiles. So why is this important? This information about the emission of greenhouse gases into the atmosphere is critical for the prediction of climate change. And in fact, this going into more detail, there is a company that makes these systems, which are basically a quantum cascade laser with a multi-pass cell. And typically in this structure, it has two different devices here. And the company is called Aerodyne, based in Connecticut. And these, for example, are the trace gases that they have measured. So a lot of detail, and not only the species that I mentioned, but also other more rare species. Okay, so this is a real important platform for application to atmospheric sciences. And in fact, I want to show you a plot of the measurement that Steve Wofsy group at Harvard did using quantum cascade laser in the case, for example, of carbon monoxide and carbon dioxide here. This is the altitude. Okay, this is the latitude. You see, this is literally what the plane does. Okay, and these actually were the first measurement. They are now maybe 4 or 5 years old, but it's continuing work, basically. The measurement resolve the vertical and horizontal structure of the atmosphere, and they provide a high resolution section, cross section, essentially, if you like, a chemical cross section of the key gases. And you get new information about not only the location, but the strength of the emission of greenhouse gases to the atmosphere, and also non-greenhouse gases. CO2, at least technically, is not considered a greenhouse gases, so it's definitely stuff you want to try to minimize. Quantum cascade laser have been sent also on Mars on the Curiosity robot, okay, for the detection of methane. And they have been used. We had collaboration for about, I would say, over 10 years with Bob Curl, who is Nobel Prize winning chemistry for the work on buckyballs, together with Crotter and Smalley. But as he pointed out, you know, that for him was a side project. Most of his research was as spectroscopist on all kinds of chemicals. So we collaborated for many years. This is an application for the detection of ammonia in the exhaled human breath. And you see, they were able to detect, in this case, parts per billion in volume. Now I want to go to the collaboration, and this I will set the tone for how we started on flat optics. So my collaborator, Jim Anderson, just to know, is a distinguished chemist who essentially one of the 2 key people that wrote the Montreal Protocol for the control of the ozone hole. And we have been collaborating for many years, starting when he visited me at Bell Labs, continuing here at Harvard. And he's interested in particular now in methane. So there is the permafrost with the tundra, and particularly as it warms up, there are these literally plumes of methane. And sometimes for plumes that are particularly kind of in tense, they light up, and you can actually see them with the naked eye. The way to detect them initially was to use this low-flying plane. At least I can fly basically maybe down to 10 meters from the ground. They're typically manned by military pilots, veterans from the Vietnam War and other wars like the Afghanistan. It's really a dangerous business. So recently, Jim has moved to drones, to use drones. And so that's Jim Anderson, drones for the detection of chemical in pervious region. Methane is a particularly very bad greenhouse gas. Why? It is 20 times more powerful as a greenhouse gas than actually carbon dioxide. And there are teratons, about 40 teratons, that are trapped in the tundra. As temperature raises, essentially more stuff comes out, and the worry is on at some point, could there be a sudden release of methane? Possibly so. So they really want to investigate the distribution of this and to use these very low-flying drones, okay? And here comes the key question. I remember one day Jim Anderson asked me, says, Federico, can you eliminate the lens in front of the quantum cascade laser? I have hardly any space for it in my drones. And honestly, when he asked me that question, I know he's a very smart guy, but this question doesn't make much sense to me. Why doesn't it make much sense? Because the divergence of the quantum cascade laser is much more than a semiconductor laser. You typically get in the vertical directions here, plus or minus 40 degrees, 30 degrees. Sideways, it's a bit less. So I said, what the hell? I mean, I don't think that's possible. But then I said, you know, why not? He's a smart guy. This probably is a good question. So I locked myself up a weekend with one of my postdocs, Nanfang Yu, who is now a professor at Columbia University. And we came up with the following solution. We said, why don't we fabricate a lens directly on the facet of a laser, a collimating lens? Okay, we don't have to have an outside lens. He wants a collimated lens. So we did this. This is on the cover of Applied Physics Letters. And that was really the start, because that was a flat lens. You can say, how can, and it was a metallic lens, you know, in the mid-infrared, the metals have little loss. And so we put a thin dielectric layer on the facet of a quantum cascade laser. On top, we engineered the collimating lens, and that was it. That was the first flat lens. Okay. Then it lied dormant. We published a few papers. We wrote some proposals. They didn't get funded, as often happens. I don't have to tell this crowd what happens with proposals. So eventually, if you try kind of enough time, eventually you get some proposal funded. So I forgot about this. But then the thought started to haunt me again. And he said, why can't I make, you know, these lenses are aberrated. I mean, showing the focal point like this is a fantasy, right? Because the outer rays get focused in different points here. So we get spherical aberration that you can compensate. But the way you have to do it is by making an aspherical lens. You see, where the curvature here changes sign. And so in this way, yes, you can eliminate spherical aberration up to a certain point, not really too precise. So my first question is, can I make a flat lens where I eliminate the spherical aberration? So everything really, I can get a diffraction limited spot. And the answer was actually yes, we did it with actually metals. This was about 8 years ago. And I want to give you this picture. What are these structural surfaces? We call them metasurfaces, and they allow basically complete wavefront control. So you have to think that this is a structured surface where you have elements. We can call these meta-atoms. They can be dielectric elements. Certainly, if you want to go to telecom wavelength and the visible, there's no choice. You have to go to dielectric structure because meta are just too lossy. But for the mid-IR, you can live well with a metallic let's say, meta lens. But in general, these meta surfaces can be engineered to have complete wavefront control. And here's qualitatively how it happens. You use the Huygens-Fresnel principle. Each meta atom is a source of wavelets. And then by engineering these meta atoms, which at least the most important control is the phase control. You can also control the amplitude and the polarization, but for the time being, let's think about just the phase control, okay? So you can literally engineer these wavelengths by changing these wavelets, these pillar size. If you change the pillar side, you change the overlap factor of light with this. But then the effective index seen by here is dependent on the diameter. If you have a larger diameter, of course, you see more of the material, so you have a higher effective refractive index. So in this area, you can do this dispersion in engineering, which really is a key feature of meta-optics. There is simply no way to do this with Fresnel optics. I want to be clear about it. I don't want to badmouth Fresnel optics. We'll have always some interesting type of application, but meta-optics can go well beyond the capabilities of Fresnel optics. So you can engineer the wavefront in an arbitrary way just by using qualitatively Huygens-Fresnel principle. You take the envelope of these wavelengths that you can design, you can model, and so forth. You know, this is lithographically controlled, optically thin, and the control of aberration is actually much easier. So in 2016, that year, I decided I want to go to really make a nice dielectric meta lens, and we did one. And without operating in the visible, using which material? Titanium dioxide. Titanium dioxide is a material which can be is basically totally transparent in the visible, has a reasonably high refractive index, around 2 to 2.5 across the visible. And so we made a nice lens like this. This shows an actual SEM picture here. You can make really vertical walls. The size here, the height of the pillar, 600 nanometers. The width can vary from, 20 nanometer to whatever you want, basically. And this is a combination of atomic layer deposition and e-beam lithography in this case. And we showed, in fact, that we could get at some wavelengths very essentially arbitrarily close to the diffraction limit. We compare this to an objective, and you see, basically, we actually could get better spots than an objective. This is not surprising, because an objective contains multiple lenses, and even in the state-of-the-art one, there are the control of the aberration is not perfect. With a meta lens, I would say what we have shown is you can correct a third order aberration, spherical, astigmatism, field curvature, and coma, particularly means when light comes at an angle. We didn't bother about correcting for distortion, because that's typically done by software, at least in high volume application like cell phones. So this was very encouraging to us. We then managed to make an achromatic lens, okay, that could, focus diffraction limited, let's say from the blue to the actual red. You see, and it's much better than a chromatic lens here. And for that, we had to use a sophisticated dispersion type of engineering, basically. Now, these lenses, I must say, while the flat lenses, the electric lenses that can focus single wavelengths, are manufactured now for high volume application. I will give you more details, okay? Not so yet for the achromatic lens. There is still research going. We are not at the stage, yes, that you could say in a year or two, this is going to go into some practical type of application. The good news now is that a lens that is optimized for a single wavelength has huge type of volume. For example, the lens is used for face recognition in cell phones, like the iPhone, are basically optimized for a single wavelength around the wavelengths of a vertical cavity single electron surface emitting laser, which illuminates your face, and that's a wavelength around 1 micron wavelengths. If you, for depth sensing in your camera, in your cell phone, you have cameras that sense the depth. You don't need an achromatic lens. You just need basically something that is operational at one particular wavelength and so forth. We did demonstrate with these achromatic wavelengths also white light focusing, basically. And so this is now the vision where we are at now, okay? The key point, and I will show you, you can manufacture now these lenses with the standard lithographic techniques used to make chips. And this is called deep UV lithography. And now things are moving also to extreme UV lithography. Okay, so that is very important, because the same foundry that manufacture the camera sensor, the chips, can now manufacture the lenses. This is not some futuristic thing. I will show this is happening as we speak, and it's very exciting. Okay, now from the point of view more of the science and so forth, because metasurfaces can provide arbitrary control of the wavefront, okay, you can achieve multifunctional metasurfaces, okay, that, for example, can operate depending on the incident wavelength, either as lenses or as other components. So the sky is really the limit in terms of research, okay? You can create arbitrary vector beams beyond the capabilities of what spatial light modulators can do it. And I need to put this line here, and the importance of inverse design and artificial intelligence in the design of optics. You know, as a physicist, I like in intuition, simple models. Fortunately, a few years ago, I saw it coming. I say AI is going to have a big impact, because if you want to design a large lens with the functionalities and so forth, you have to go by inverse design type of techniques. Basically, you have to specify the function that you want and basically work backwards for a series of loops. And then the effort, you still need the physics to understand what your program has actually done. And it's not easy. And it's humbling for a physicist to recognize that our intuition has limits. These methods are very powerful. They're here to stay. So I told my group, we better move fast on this. So the fabrication process, deep UV lithography is known. It's a deep UV stepper. It's widely used in projection type of lithography. So I moved the fabrication of these lenses because I wanted to have really an industrial impact. And so this is actually the initial work that we did. An all glass metal lens with deep UV lithography. You see, we showed actually diffraction limited focus here at one particular wavelength in the red. This was all glass. But these are 160 million nanostructure. These attracted really the interest of industry. That was my goal of this paper. I wanted industry to pay attention to this, because until we do this bi-beam lithography, they are not going to care. Okay, so that's what we did, and it had an effect. So later, DARPA asked me, Federico, why don't you go for an application like 10 centimeter? So this was done up at the Cornell facility by deep UV lithography. It's very recent work, and this shows a comparison. You see a metal lens and a conventional refractive lens. You see the advantages. Obviously here, it's the reduction in weight, more than a factor of 10, the reduction in thickness about a factor of 50, and other type of advantages. So there are some interesting scientific type of application and military ones also of these large lenses. And so my students played to mount them on a telescope on the top of our institute. And because we said we want to see what we can do. So we put a filter here. Okay, this was to just look at this to get rid of the background. And they imaged, a nebula, a North American nebula. Now, we are doing pretty well. If you go online and you look at the images, with this kind of telescope, I would say we are doing at least as actually better. Okay, and it's pretty obvious why. I mean, we are doing it in a much simpler way, thinner, and the control of the aberration is definitely more precise, and it ultimately costs less, which is important for high volume type of application. With that, I do not want to say, the message is not that meta-optics will replace refractive optics in everything. That's complete nonsense to say that. But it will capture large sectors, particularly in the consumer electronics area. This is happening right now. And how do I know? Well, you have to wait, because I'm going to tell you then about a company that I started and what we are aiming at. This is the most recent work we have done, is this year. I got interested. That the Nobel Prize in Physics was given essentially for attosecond science. So we got interested in that because I said, let's try to do really something very challenging. Let's see if we can make a metal lens in the XUV here. So we teamed up with a group at actually University of Graz. I'm going to say that in a few minutes, okay? And basically the idea is, look, when you work in the XUV, first you work in actually vacuum, okay? Second, you quickly recognize there is no really good optics. You don't have really lenses yet. Most you have Fresnel zone plates, which have problems in the quality of focus. We did some modeling so a metal surface is ideal for that. But here, again, because the challenges of the wavelengths, we decide to go, we only use a silicon platform. But silicon, what happens here when you actually are, if you look at the refractive index, the real and imaginary pair, you quickly realize in the XUV of interest, around, tens of nanometer and so forth, the refractive index is less than unity. So one of my postdoc, Marcus Osiander here, this is the paper that was just published, had the nice idea to say, let's use vacuum as the focusing material. Basically, the refractive index unit is greater than silicon, so we can make a focusing lens. Of course, the fabrication was very hard. I mean, I'm not claiming that any application of this technology is anytime soon. It might take 5 to 10 years, but it's important and existence proof here. First of all, when we designed the metal lens, we quickly realized, you see, we can get a very nice focus. Here, the intensive transverse direction as opposed to something spread out, okay? And this, again, I showed already. Well, this, again, this is the advantage. We call this EUV focusing by vacuum guiding, okay? And we were really fortunate to establish collaboration with Martin Schulz. Martin Schulz did his PhD with Ferenc Krauss, who was one of the Nobel Prize winner at the Max Planck in Garching. And in fact, his experiment was to measure the time scale of the photoelectric effect. That is one of the achievements that was mentioned by the Nobel Committee in the press release. So I'm not going to give you any details of the optics here, except here that basically what is not shown is there is a dispersive grading here. So essentially you create the attosecond light, the high harmonics by focusing a near infrared femtosecond laser in a noble gas cell like argon. So you create the odd harmonics, many odd harmonics. This is in fact was first done by Huillier, who co-winner of the Nobel Prize this year. And basically here the setup picks up the 21st harmonic, which is 50 nanometer, and then we actually study the focusing. This is a structure fabricated by my people here. It was a really tremendous effort just to get it going because they break so easily. You can imagine ultra thin and so forth. And the technique to measure, you know, there's really no optics to do it. So we use the conventional knife edge technique, which in fact I used during my doctorate at University of Rome. It's a nice old technique which works well. Essentially, you have a nice edge, you move it vertically, horizontally, and you can get basically the actual beam waste, okay? So I think this is actually quite promising. I want to go in the applications. When we got the first dielectric lens to work, I talked to my student then, Rob Devlin, and said, we have got to start a company. This is the right time to do it, and we did. This is Metalens. With a target, the high volume consumer electronics market, we are now 35 employees on base. We are completely fabless. And who are the fab now? The fab is one of the major foundries that make chips. That's the exciting part. You see our supporters, essentially there is venture capital, but there is a strategic type of investor, Intel, of course, Applied Materials that makes all the equipment for integrated circuit, 3M. Basically, the vision is meta-optics can be, it's more than a vision, it's happening now as we speak, okay? It's going to enter the consumer electronics market. The camera module in cell phone, particularly for applications such as face recognition, depth sensing, the whole technology will be made by these foundries, not only the semiconductor chip, but also the lens, the flat lens on actually top. And this tells you a bit. You know, I obviously cannot say a lot here. Essentially, it's a single lens, or maybe at most a couple of lenses and an aperture, but you can show a single lens properly designed and an aperture can correct spherical aberration, field curvature, astigmatism, and actual coma. Okay, so this is a conventional sensor. You see, yeah, this is widely available commercially, but it's quite complex. The alignment is critical. You have lenses of different material, and the intensity fades out at the edges. This is just the physics of refractive optics. You can design a metal lens as telecentric, meaning that the intensity is basically uniform or almost uniform up to the edge. And you can see a comparison here with a sensor that contains four plastic lenses, conventional. The intensity you can see fades away. Here you have increased brightness and intensity is uniform. So that's a key advantage. Besides the simplicity, you know, the ease of alignment and so forth. And this, in fact, was announced this year. Metalenz announced a partnership with UMC, is one of three major foundries based in Singapore, for high volume manufacturing of optical lenses using commercial semiconductor processing platform, and enables an easy application, smartphone, laptops, also the automotive sensing. So this is happening now. In fact, unfortunately, I cannot tell you in which cell phone it is. This is proprietary information, that you can start to find metal lenses in some of the existing cell phones. And so this is the general impact. I think there is impact beyond what I said, smartphone, also wearable displays. We have made some high quality RGB lenses, in fact, 1 centimeter diameter. However, I would say that for application that virtual reality is a limited volume, and augmented reality is still not here yet. Augmented reality means to merge the virtual with the real world. It's not there yet. It's been a lot of work, like the Google Glass. We are not there yet, but certainly I think meta-optics can contribute. With its stuff on stretchable material, we have recently made a high-quality meta lens directly on actually PDMS. And that's actually very exciting. Okay, there are applications in fiber optics and so forth. We are working with Corning for application mode multiplexer. This is for the near infrared. And for the mid infrared, one of the advantages, of course, is that the quality of materials, the mid IR is not that good. So there's still a lot of work to be done in the mid IR. And at the end of the day, none of this work would have been possible without a large number of extremely talented postdocs. Some are here. They've been with me 5 years now. They're on their own, starting, in fact, both of them, their own companies. Others, a student and so forth, and some professor who are direct collaborator. I want to mention for the design part, for the AI part, very fruitful collaboration with Professor Steve Johnson at MIT, okay, Professor Xing Chen at Boston University, and Professor Douglas Werner at Penn State. With that, I'm done, and I really am very grateful for this honor. It's always been nice to be recognized at home. Thank you again for your attention, and I'm perfectly happy to answer questions.
Thanks a lot, Federico. I don't know if we are a little bit late in time, but I mean, if there is some short question from the audience, maybe let's move to the award ceremony because it's quite late, and I know that Professor Capasso has an appointment now. And so I invite the director of ISM, Antonio Crescenti, and so ISM is proud to award the PRISM 2023 to Professor Federico Capasso for the breakthrough achievement in the last 5 years in the fields of science of matter. Thanks a lot.
Thank you.
Federico, we will ship you the award, and as you were showing, I mean, this is really it witness that you are really doing active science innovation even the last 5 years. So now, beside your career, which is quantum cascade laser, but still keeping pushing the science beyond the limits. Thanks really a lot.
Thank you. No.
And now the next prize Next prize. So we are proud to award the PRISM 2023 in the junior category to Nicola Gasparini for the breakthrough achievement in the past 5 years in the field of science of materials. Thanks, Nicola. And as you said, I mean, we are really like to have you in the senior category very soon. So keep innovation and push the science as you are doing greatly up to now. Thanks really a lot. And I really like to thanks all the people that were working night and days for selection, but also for setting up the award ceremony and the prize. And one for all the team of Gianni Parisi and the communication office of ISM. Please, I ask all the people who were involved in the communication office to stand up and then to make a big claps to them. Okay, thanks a lot. I mean, the award ceremony ends here. Very soon, at the beginning of the next year, we will spread the request for nomination for the 2024 PRISM Award. Thanks really a lot, and I ask all the people to come here to make a photo all together. Thanks.